All right, so it looks like we're recording now, and let me get the screen share up. So for people that might be interested in this, you can bring this up. I will share it when the time comes. So in the OpenStax book, we have the regular table of contents. You should be familiar with this point. We've been going through the weak acid, the weak base, equilibrium constants, the solubility. If you go underneath that, there's standard electrode half cell potentials. This is going to be a chart that we will be utilizing in electrochemistry. So I'll bring this back up later today when we get to this point, but it might be a very useful page to bookmark and to have up while we're having these types of discussions. So with that being said, I'm going to go ahead and minimize that, and I'm going to bring up the whiteboard content. So if you remember, the last time that we were lecturing, the primary thing that we were going over for electrochemistry was balancing redox equations. And specifically, when we were balancing redox equations, we were balancing them in acidic medium. Now, when we take a look at this, I mentioned we could also do it in basic medium, meaning there's hydroxide instead of H plus present. So what we're going to do now is take a look at how we would balance an electrochemistry redox reaction in basic medium instead of acidic medium. And it actually is that you have to work through this, go through the acidic medium content, and then neutralize any acid content with hydroxide. So those are the steps that we're going to look at. So here's the problem. Write a balanced equation with the oxidation of iodide, that's I minus, with the permanganate ion. So the permanganate ion is MnO4 minus. These are all common ions you should be familiar with from Chem 111. Okay, it's in basic solution. So when it's acidic, we use H plus. When it's basic, we'll start with H plus and then we'll use OH minus to convert any H plus material to water. Okay, and this is going to yield iodine. This is the neutral form. It's one of the diatomics. And manganese oxide, which is the form manganese 4. So you need that in terms of oxidation numbers when we're getting ready there. And this would make for MnO2. All right, so if we take a look at all of this and we put it into a basic unbalanced equation, all right, it's going to be MnO4 minus plus I minus is going to yield the manganese oxide plus iodine. All right, now we start with our half reactions. So we're going to have an oxidation and we're going to have a reduction. At this point, you're going to need to know what's being oxidized and what's being reduced. Now, I chose this example specifically because now, in the previous example, it was more obvious what was gaining an electron and losing an electron when we had the iron in that previous example from the other day. But here you've got two negative charges and they're both becoming neutral in some format. So you need to be able to pay attention to which is being oxidized and which is being reduced. All right, so in this case, if I have I minus, it would have a 1 minus charge. And if I have I2 here, this would be going to 0. So what would be happening here? Is this a loss or a gain?
It's a loss of electrons.
Thank you. Okay. Keeping in mind that electrons are negatively charged, if I go from a negative charge to a neutral charge, I have lost some of the electronic property. So oxidation is loss. So this will be my oxidized portion. It's going to be I minus goes to I2. All right, and that means that the reduction, now I'm not going to force you right now to go through the oxidation numbers, but you should be able to do that for the manganese and see that manganese is the reduction portion here it's going to gain. All right, and we have manganese O4 minus is going to go to the manganese oxide. All right, so these are the half reactions. Now, it's important when we consider half reactions, we need to add what? Electrons, right? Because this is a redox reaction. So for the electrons that we need to add here, the iodine one is going to be fairly easy. All we need to do is say, well, there's been a loss of 2 electrons. So I minus is going to become I2 plus, and now we start to balance it. So if there's 2 iodines on the right, there's 1 on the left, I need a 2 here. Okay, so if I multiply this whole entire reaction by 2, I'm also going to have an electron in here, right? And so, wait a minute, I'm not doing that, sorry, because I don't need 2 of the I2. So, jumping ahead of myself. I just need a 2 in front of here, not the whole reaction, okay? But what's important here is that since I have 2 of these, in order to create I2, there are 2 electrons that are being given off. All right, so now we need to head to the reduction portion. The reduction portion is going to be a little bit more involved because there's an oxygen. So the first thing we do for oxygen is we balance with water. So I need to find out which side requires more oxygen, and it is the product side because I have 2 oxygen on the product side. I have 4 oxygen on the reactant side. So in order to help balance that, I'm going to add 2 water here to bring up the total to 4 oxygen. So now I've got 4 oxygen on each side. So now, continuing as if we were going to balance this in the acidic manner, I would now say how many H pluses do I need? Well, here I would need 4 of them because I put 2 waters, so that's a total of 4 hydrogens. So I would say I'm going to use 4 H plus, okay, plus the MnO4 minus gives me the manganese oxide plus the water. All right, so this, the last thing we need here is going to be the electrons, right? So the total number of electrons that are going to be transferred here, we have to figure out the number at this point, right? The charges. So somebody take a look at this and tell me how many electrons are needed.
Would it be 3?
That's correct. All right, 3. Now, where does that come from? Well, this is neutral, okay? But over here, I've got a total of 4 plus because of the hydrogens, and I've got 1 minus. So in order to make this neutral so that I have neutral over here and neutral over here, I need to bump up my negative charge by 3. So I go ahead and add 3 electrons there. Okay, so it'll be plus 3 electrons when I get to the net equation. Right, so now, I'm sorry, I was jumping ahead of myself before with the iodine. Now we need to take a look at everything and do the multiplication through. All right, so here we said the iodine is going to be 2 I minus for the iodide, and then that goes to iodine plus 2 electrons. So you can see the common factor we're going to have here. You've got 2 electrons and 3 electrons. We're going to need to go to 6 electrons to get them to cancel. All right, and then over here on this side, we're going to have, and I'm going to back up some because I have a lot that I need to write here. We're going to have the permanganate ion plus, I need a 4 in front of that, plus 4 H plus 3 electrons, right? The electrons should always be on opposite sides because they're going to cancel out. So then this would yield the MnO2 plus 2 H2O. Now we multiply through in order to cancel the electrons. So this is going to get a multiplication of 3. This is going to get a multiplication of 2 because what we focus on is a common electron transfer. So we're going to get 6 electrons when we distribute that, and those electrons will drop out. So then I carry through and I multiply to everything, and I end up with a net reaction. Now keep in mind, this is still acidic, so we haven't even gotten to the basic portion of this yet, but that part is less complicated. That basically just wraps it up. All right, so it's going to be 6I minus plus 2 of the permanganate ion, right, plus 8 acidic protons, okay, electrons drop out, is going to yield 3 of the molecular iodine plus 2 of the manganese oxide plus 4 molecules of water. And that is the net reaction here. So if you were asked to solve this in acidic media, you would be done at this point. This would be your net reaction. But because this is not acidic and it's basic, we're being asked to take it another step further. And what you need to do here is get rid of any acidic medium using a basic medium. So here's the acidic portion. What I need to do is add hydroxide. So I'm going to add 8 hydroxide in order to get rid of all the acidic medium that's present here. But what I have to do is anytime I add to one side of the equation, I need to add to the other side of the equation. So what you're going to end up with is you're going to have a canceling of acidic medium here. It's going to form water, but then you're going to have excess hydroxide left on this side. And now you are inside of a hydroxide-based medium instead of an acidic-based medium. And that's how you balance this in basic medium. So it's really only one additional step. You want to really focus on mastering how to do acidic medium because that's 90% of the heavy lifting here. And then the last 10% is just doing this little maneuver with the hydroxide. All right, so let's consider what's going to happen then. We would still have 6 of the iodide. We would still have 2 of the permanganate ion. Okay, but now I would have 8 water. Now, if I have 8 water, I have to keep in mind that I have 4 water on the other side. So just like the electrons, the water that has a commonality is going to need to drop out. So all 4 water molecules over here are going to drop out. Okay, and that means half of the water molecules over here because I'm going to get a total of 8. If I add 8 H plus to 8 OH minus, I get a total of 8 H2O. 4 of those will drop out with the 4 that are over here, and so I end up with just 4. Okay, so that mini portion that I just talked about there, we're talking about essentially spectators or net material that needs to drop out. All right, so then moving forward, I still have the 3 molecular iodine. I have the 2 manganese oxide. And now I would have 8 hydroxide ions. And so you can see, if you take a look at this, I still have the manganese and the iodine, which were the original oxidation reduction material. But now, instead of it being an H plus, like we learned last time, and is shown up here, we now are sitting in a basic media. All right, so the last step is just simply flipping your waters and making sure that you introduce the hydroxide material into this. So with that, I'm going to pause here and ask for any questions regarding balancing the redox reactions in base material. Are there any questions? Everybody feel good? Okay. So if there's no questions on that, I'm going to move on to looking at how we can actually start developing batteries or making use of redox reactions. So all of the reactions that we have discussed so far are the transfer of electrons. Now, what we're really interested in when we start talking about electrochemistry is how can we harness the transfer of electrons to actually do some useful electrical work. And that's where we get into the concept of batteries. And batteries are really formally called cells. So you're going to hear the term cell being used quite often here. I may interchange it with battery on occasion. Okay, but there are 2 major types of cells. There's what's known as a galvanic or a voltaic cell. Those are used interchangeably. All right, so that's spelled Galvanic. Okay, and again, you may hear it referred to commonly as a voltaic cell. So we think of volts in batteries. All right, and then the other one, which we will not be discussing today, but you will have material on that I'll deliver at some point, is known as an electrolytic cell or electrolysis. Okay, so that one will be down the road in a little bit. So we're going to take a look at galvanic cells, which are the more common cells today. So to represent how a battery or a cell works, we're going to set up somewhat of a crude drawing, and we're going to explain everything that's going on in that drawing. So first of all, you're going to want to have two containers. So these are my horrible representation of beakers. I'm by no means an artist. Right? And we're going to have some solution in each of these beakers. And we're also going to have two metal, what we call electrodes. So you may see these sometimes represented as metal rods. They may be metal plates. Okay, these are going to be our electrodes. And electrodes are some sort of solid metal that are going to be responsible for this electron transfer as we're going back and forth. Okay, so in the example that we're going to use to start, we're going to have zinc metal. So I'm just going to put Zn for this one here. And then we're going to have copper metal as our other metal here. Okay, and they are going to be sitting in a common solution of whatever the metal is. So for zinc, we're going to have zinc 2+ ions that are being generated and utilized in a solution of zinc sulfate. And same for the copper. We're going to have some copper 2+ ions that are sitting in solution. So you can consider these aqueous electrolytes, and they are going to be hanging out in a solution of copper sulfate. All right, now we're going to connect a wire, okay, most typically a copper wire, but you can have other sorts of wires. And the wire is going to be hooked up to the electrodes. And right here, we're going to have some sort of a device. Okay, so in many books, you're going to see this pictured as a light bulb. It might be a radio or something of that nature. But what we essentially want to do is pass electrical potential through the form of electrons to the device in order to power it. And then the electrons can be brought out and down into the opposite solution, right? Now I'm setting this one up in a very specific way. The electrons are flowing in one direction. They don't go back and forth very readily. They tend to go in one direction, okay? And then when you are setting this up, you need to know which metal is going to go in which portion of the cell. And that's going to be referred to as the cathode and the anode. So we'll talk about that separately in just a minute here. Right? But there is one very important piece missing here, and that is that we need some way for positive and negative ions, okay? Because we are going to have SO4 2- generating. There's going to be a buildup of positivity wherever the electrons are being lost, right? Because every time I send an electron away, there's a positive charge left behind. So I have to be careful. If I build up too much positive charge or I build up too much negative charge at one of the cell half potentials, then the battery or the cell is going to stop generating proper electric current. So in order to avoid that, I introduce what's called a salt bridge. So a salt bridge is going to connect the two solutions. Many times in a lab, when you're making crude batteries, you're going to see this as an upside down U-shaped, maybe glass pipe or bar or something of that nature. Okay, and inside of here, you're going to have some positive and negative electrolytes. So potassium chloride is the example I'm going to use here, right? So we can generate K+ and Cl-. And these are going to be very important because if there's an area that has a buildup of positive charge, I can send over some of the chloride ion to help balance that out. And if I have an area that's got some negative charge buildup, I can send over some potassium ions to help with the buildup of charge there. So you don't want a massive buildup of charge in one of the two half cells that we have here. And that's why the salt bridge is so important. If you don't have a proper salt bridge or something to basically communicate and even out between those two half cells, you're going to have a short-lived battery that's going to fail to produce proper electric current after a small period of time. Okay, so the term that we used a minute ago was anode and cathode. So these are going to be in relation to oxidation and reduction. So in this case, zinc is sending out electrons with the flow of the battery that we have here. So that means that I would expect zinc metal to go to zinc solid, okay? Or zinc 2, I'm sorry, to go to zinc 2 plus. There we go. Okay, so this is the general process I'm expecting, because when I do this, I'm going to liberate 2 electrons that can pass through to my device, right? And when we have this oxidation occurring, wherever the oxidation is happening, this is known as the anode. So this left portion with the zinc here, this is the anode for my battery. Okay, and then we also have the cathode portion of the battery, and the cathode is going to be over here. The cathode is where the reduction is going to occur. Okay, so the reduction being that I'm going to have, and I am writing faster than I can keep up with here. I'm going to have copper 2 plus going to copper solid, right? And so this means that I'm going to gain the 2 electrons that zinc sent over, right? And it's going to become solid copper. So I can expect, you can sometimes call this plating. I would expect that copper 2 plus is going to adhere or plate itself to the solid copper, right? Whereas the zinc electrode here, I would expect that it's actually going to remove zinc metal and create zinc ions in this process. Okay. So if you ever have trouble remembering this, remember that in the alphabet, A comes before C and O comes before R. So the anode is where the oxidation will occur, and the cathode is where the reduction will occur. So just map out the alphabet if you ever forget. A is going to come before C, and O is going to come before R. So the A and the O get matched together, and the C and the R get matched together. That's the easiest way I usually tell students to remember this. But you need to know where oxidation occurs, the anode, and where reduction occurs, which is the cathode. Right? Now to make things even more complicated, okay, because this isn't complicated enough already, when you start talking about things that are oxidized, they are referred to as reducing agents. So they are agents of reduction. Now, that's the case because if they are oxidized, they are allowing the reciprocal, the copper in this case, to be reduced. So they are known as reducing agents. So in this case, zinc, which is being oxidized at the anode, is known as a reducing agent. Okay, and this will usually confuse students because reduction and oxidation are opposite. So we're using the term reducing for something that's being oxidized. Okay, so the zinc is the zinc is not reduced even though it's a reducing agent. It's allowing something else to be reduced. Okay, and then that means that the copper over here is known as an oxidizing agent. And these terms are important because when you start looking at certain charts, they will list the reactivity of different metals, and they'll say, if you go down this way, it makes for a better oxidizing agent, or if you go up this way, it'll make for a better reducing agent. And you have to understand what it's referring to if you come across a table or a problem like that when it says reducing agent or oxidizing agent. So anytime you see the term agent, you need to realize what's happening is actually the reverse of what's being stated there. So a reducing agent itself will be oxidized, and an oxidizing agent itself will be reduced. All right. So that is the basic setup for a battery or a galvanic cell. So what you're going to do is once all of this is hooked up, it's all chemistry at that point that's going to be occurring. You're going to have the zinc that is losing electrons. It's passing them up through and giving some electric potential to the device to power it. And then the electrons can be deposited into the copper solution where the copper can be reduced. And this is how your batteries work, the same type of batteries that you would get at a store. It's not designed up in this crude beaker system, even though this will work. Usually they have an outer layer and an inner layer. So maybe the outer layer has zinc, and then the inner layer, one of the more common ones is a manganese oxide, like we've been working with for instance, a AA battery. So a double A battery has about 1.5 volts that it generates, and that is through a zinc and a manganese oxide redox potential when you look at that. Right. So then same thing for a 9 volt. That's obviously got more voltage going on here. And that's one of the things we're going to head into in a minute is what's called the voltage or the cell potential. So how much electric current can I actually generate as I'm taking advantage of these reactions? So I'm going to pause here for 1 second just in case there's any questions with this setup and everything going on here. All right, in general, I'm not hearing anything at the moment, so I'm going to go ahead and keep going then. All right. So the next thing that I just want to mention briefly is that it is very important when you set up these cells that you have half cells, and we've been breaking this down in half reactions. So you need to keep, even though they are working together through electron activity, you need to keep the zinc and the copper separate in a situation like this. So I'm not going to be able to effectively generate a battery if I were to take zinc and copper and put them into the same beaker. So that doesn't mean that there wouldn't be any redox activity going on, because I could have copper 2 plus and zinc solid, right? And that would go to copper solid and zinc 2 plus. So this is essentially the net reaction of what's going on here, right? So I take some solid zinc and I generate zinc 2 plus. I have some copper 2 plus and I generate solid copper. This is going on in 2 separate beakers through electron transfer. But if I put them all in the same beaker, then the electrical activity is just going to go and exchange between the 2 metals directly. The goal of the battery or the cell is to isolate the electronic activity outside of solution in order to power the device. Right? So I just wanted to bring up that one side note that it is important when you're setting this up. It can't just be dumped into the same cell potential. You have to have 2 half cells in order to create the whole cell potential here. All right. So when we have this type of setup, I think I mentioned this a minute ago, but I'm going to reiterate this here because this is very important. Your cations, so anything with a positive charge, is going to move towards the cathode. Okay. So the reason for that, if we go back up and look, is that when we take a look at what's going on in the cathode, there are electrons that are being removed from solution, right? So you've got copper 2 plus, it's gathering up electrons in solution, and then it is going to create solid copper. So if I'm removing negative material here, then that means that I would have a migration of any cations available towards that area to help balance that out, okay? And then when I have the anions are going to move towards the anode. Okay. So this is because I have a positive charge that's building up over in the anode. Okay. Whereas in the cathode, I've got all the electrons that are piling up. So I've got a negative charge that's building up over in the cathode. Okay. So the salt bridge, again, just to reiterate its importance, is going to prevent the excess buildup of positive or negative charge at either the cathode or the anode. All right, so let's talk about cell potential then. So we've been setting up this battery, but we want to actually know what we can get out of the battery, and that is known as the cell potential. There are a lot of different names that cell potential is given. So cell potential, you may hear it referred to as more commonly voltage. Okay, so you talk about what's the voltage of a battery. You're talking about the cell potential of the battery. Sometimes it's also known as EMF, okay, where EMF stands for the electromotive force. And then sometimes EMF is abbreviated as just a capital E. So this is sometimes referred to as the E cell, or the electronic potential of the entire battery when we talk about cell. Now remember that the cell is split into two halves. So each half will have its own potential, and then when you combine them together, that's where you end up with the potential for the cell, right? So this is really going to be the electric, no matter what you call it, this is the electric potential that the battery has. Okay, so how much power could that battery produce or generate? Now, because we have all sorts of different metals that we can utilize, it becomes very inconvenient to represent batteries this way. So I wanted to draw through this one time so you could understand what was going on. But most of the time, if you were to set up a problem and you wanted to represent this, you don't want to always go through and have to draw all of this. Although this is a good exercise for a quiz or a test question where I could give you something and say, set up a battery for, you know, maybe there's something else, zinc and some other metal, okay? So the way that we can represent this is you start by representing the anode portion in writing. Okay, you separate it with a double line, and then you represent the cathode portion. So the double line really represents the salt bridge that's going to be in between the two half cells when we're working with these. So when we want to write this out, you have to remember there's two parts. There's the actual electrode metal, and then there is the ion or the aqueous form of that metal when it's liberating or receiving and gaining electrons. So the way we would write the above battery would be zinc solid. So that's the electrode, that's the starting point. And then we put a single line to represent a barrier in the phase, meaning it's no longer going to be solid here. So this goes to zinc 2+, and you're normally going to see a concentration in here, okay? Because these solutions are going to be at a certain concentration. So we need to know what the molarity is. Now we're going to talk about standard cell potentials today. And when you're under standard conditions, similar to when we talked about thermodynamics, you have to be at 1 atm, 25 degrees Celsius. You're going to have standard conditions if you want to use tabulated voltaic measures, or what they call reduction potential. So we'll get to that in a minute. Okay, but the molarity is typically going to be 1 molarity if you're using standard values here. All right, and then salt bridge comes in between. Now, after the electrons have been passed from the zinc, they are received by the copper 2+, right? And when the copper 2+ receives those electrons, barrier, okay, and this, squeeze that in there, there would be a molarity of the copper sulfate that goes to solid copper to finish off the cell here. Okay, so this is the way that I can represent everything that I just drew out in that previous not equation, but the previous visual example of the galvanic cell. So this is a condensed version, the way that we would represent this. And again, a single line is going to mean that we're dealing with a phase boundary of sorts. So you're talking about doing something that was solid to aqueous, or something that was aqueous going to a solid. All right, and then the double break is going to mean that we're talking about, this is where the salt bridge is. So this is the actual physical divide between the two half cells, and the salt bridge is how we connect them. So if you take a look at a zinc copper battery, okay, the EMF of that battery is equal to 1.10 volts at 25 degrees Celsius. Okay, so again, thinking to batteries that we use in everyday life, we talk about voltage. So you might talk about a 9-volt battery. Or you might talk about a 1.5 volt battery, which again is like a AA battery. Okay, so when we pick out the different metals, they're going to have different voltage that are associated at a standard condition. And so based on the selection of metals and the setup that we are pairing them with, that is going to create what's known as the voltage or the cell potential for that battery and how much electricity it could generate. Okay, so this right here is the cell potential for the entire setup that we have there. So one of the questions then becomes, what would be the cell potential for just the zinc? And what would be the cell potential for just the copper? Because each portion is going to have its own voltage or potential, and it's really the working between them that creates the net potential, and that is known as the E cell or the electromotive force. All right, so the 1.10 voltage is for the entire setup, not just the zinc and not just the copper, but it turns out that the zinc and the copper have their own. So the question now becomes, how can we measure the half reaction potential values? Okay, and the way that we do that is through standardization. So if you remember, when we were talking back with thermodynamics, we had to figure out a way that we could chart these standardized values, and what we needed was a 0 point, and the laws of thermodynamics allowed for that with 0 Kelvin. So it's similar here. We're going to need a 0 point that we can say this particular half reaction is going to be set equal to 0. And anything else that we measure relative to that, we will then classify that as the voltage that is generated by that half cell. All right, so what's important to understand here is that when we start talking about the E cell, or the potential for the entire cell, now you're going to see I put the little notation up there. Okay, that notation means standardized. So we did a similar sort of thing when we were talking about delta G and delta S. Okay, so the standard E cell is going to equal the standard half cell of the cathode minus the standard E cell of the anode. And this is how we can find it out. So what we're going to do is we're going to say, well, if I can take the reading for the entire cell, and that's what happens. I can't take individual readings for a half cell. I have to have the electrons being passed through a voltage meter at the top. And in order to do that, I can't have one solution like we talked about. I have to have two separate half cells that pass the voltage through the meter, and then I can get a voltage reading and associate it with something. So the key here is that one of these has to drop out to 0 in order to successfully do that, because I can get this reading through a voltage meter. And then if I know that one of these is 0, I can associate this with one of the others. All right, so that's where we're headed with this in order to standardize. And the way that we standardize is we end up using hydrogen. So hydrogen half cells are commonly utilized as the 0 mark. So the way that they do that is they end up using 2 hydrogen at 1 molarity, and you're going to see 1 molarity coming into practice more and more here as we start talking about standardizing, because everything has to be at 1 molarity when we standardize batteries. And this is 2 electrons, because it's going to generate hydrogen gas, which again is a diatomic 7. Now, when we deal with this, you might realize that hydrogen, you can have it in an aqueous form, but when we generate hydrogen gas, we don't have an electrode. So I need something to plate this onto, and gas is not going to work. Whereas copper, I can obtain a solid copper rod, I can obtain a solid zinc rod. But hydrogen is not a metal unless it's near 0 Kelvin. And we're working at 25 degrees Celsius because this is standardized. So this is hydrogen gas. So what they end up doing is they plate the hydrogen gas on an inert metal, and that metal is platinum. So platinum is very commonly associated with hydrogen. You see this when you get to organic chemistry. The food industry does a lot of what's called hydrogenation of fats, so partially hydrogenated fats. They're talking about using a platinum metal bed and then exposing the fats to hydrogen gas that are basically bound to that platinum metal bed. It's a way to trap hydrogen gas onto plating it onto a solid form, so to speak. Otherwise, it's just going to bubble out a solution. All right, so the main point here is that this potential, we are arbitrarily going to set this and say this is 0 voltage. So if I put any other half cell in with this, that means the result is going to be, that's passing through the voltage meter, is solely going to be responsible from that other half cell, okay? And then as soon as I can find one half cell, I compare it with another metal, and if I know the 1/2 cell, then I can come back up and this doesn't have to be 0. I can say, well, I can read the full cell voltage, and I know from my standardized hydrogen potential what the other metal is, so then I can start combining them. And that's what we're going to do now. We're going to take a look at how we could potentially get to finding out the half values of the copper and the zinc that we were working with. And we'll start doing that by subjecting one of them, in this case it's going to be zinc, to the hydrogen. All right. Now, you're going to sometimes see in books, this is referred to as SHE, or some people call it She. This is the standard hydrogen E cell, okay, or the standard hydrogen EMF, whatever you want to call it. It is the way that we standardize at 0 when we are at 1 molarity, 1 ATM, and 25 degrees Celsius. All right, so let's take a look at setting one of these up. I'm going to look at zinc. So I'll take zinc metal as a solid. That is going to become zinc 2+ at 1 molarity, because I'm standardizing this. Salt bridge, hydrogen at 1 molarity in solution. Hydrogen gas, platinum. So realize there's 2 lines here, because this is aqueous, this is hydrogen gas, and then this is solid platinum. All right. So this is writing out the battery or the cell for a She example, an SHE example, where I want to look at zinc and its potential. So I'm setting the hydrogen at the cathode end in order to 0 that out and find what I get. So I go through, I set up a solution like this. I've got, let's say, my zinc in aqueous solution. I then use some HCl at 1 molarity in order to generate H+ at 1 molarity. And I set up my galvanic cell. And when I pass it through a voltage meter at the top with the electron flow, I find that the value is 0.76 volts for this entire battery cell. So what I can do then is say, all right, that means that for this setup, the E cell is 0.76 volts. That is equal to the E cathode standardized minus the E anode standardized. Well, in this case, the cathode is the hydrogen, which we said is going to be set to 0. So that half cell is 0, which then only leaves the half cell for the zinc 2+ / zinc half cell. Okay, so if I take a look at this, 0 drops out. That means 0.76 volts equals the negative E cell potential for zinc. So in order to make it just the E cell potential of zinc, I have to flip that. And that means that it's going to be negative 0.76 volts equals the E cell potential for the zinc oxidation process. Okay. So let's take a look. We're going to minimize this for a second. And if I bring up the chart, okay, we're going to go down and we're going to find zinc. So this chart in the OpenStax book, and I'm openly going to admit I'm not the biggest fan of this because they do it alphabetically. Now, it helps in terms of finding it, but there are better charts out there that list these values by their positive to negative ranking. And that's going to become very important when you're handed two random substances and you have to decide which will be the anode and which will be the cathode. And that's where we're headed next. All right, but back to the point here, zinc. Now you have to look, there's a lot of different zinc here, right? You can have zinc cyanide, you can have zinc with ammonia, you can have zinc hydroxide. So you need to be picking the correct half cell. And we were looking at zinc 2+ goes to zinc. And so in order to find that, we just come across here, it is negative 0.7618. And we said in our value here, it was negative 0.76. So there you go. That's one of your standardized values. All right. Now, how are we going to find copper? Well, there's two ways we could do that. We could do the same exact thing for copper. We could set up copper in the SHE electrode situation and solve for copper. Or now that we know the half potential of zinc and we know the full E cell potential for a zinc copper cell battery, I can solve for copper that way. So that's what we're going to do here. Right now, I'm going to pause for a second. I'm going to scroll back up here and just clear the top. And I am going to just ask one more time if there's any questions, because I just covered a decent amount of content. Are there any questions regarding this? Okay, moving along. This is good in terms of keeping us on pace. So let's talk about how we're going to solve this. The way I'd like to solve this, since we just did one of the SHE examples, is we're going to go back to the original example. Right? So keep in mind that E cell, you might hear this referred to as E naught cell, that's just the standardization, is going to be E of the cathode. Now, the cathode in the original was the copper. So it's the Cu2 plus Cu relationship minus the cell potential for the half reaction of the zinc. So that's the zinc 2 plus zinc relationship. Now, the value for, if I set this battery up, is 1.10 volts. Now the question was, what were the individuals here? Now I know one of them because I separated zinc out and I ran it through a standard hydrogen electrode. And we found that that value is negative 0.76. So the way you need to write this, and you have to be very careful with your positive and negatives. It's a very simple mistake to make. Okay, we're going to have E cell Cu2 plus Cu minus a negative, okay, because this value itself is negative 0.76. So if that's the case, this is minus a negative, and that's going to affect your answer if you're just subtracting and you're forgetting to add this extra negative in here when you're pulling it from the charts, okay? So this will be 0.76 volts. Okay, negative and negative, that means I'm going to add this. So it's really plus 0.76 volts. And then if I solve for that, because that became plus, then I subtract it from both sides. So I'm going to get rid of this on this side, which means I would also take it from this side. And then I can find the E cell potential for just the copper, which I've now isolated. And this is just the positive E cell here, right? I don't have a negative value sitting in front of this like I do for the anode. And that is going to be equal to 0.34 volts. So let's see if copper turns up at 0.34 volts. So going back, I bring up my page here. I'm gonna have to go up to C for copper. Okay. And here's copper. Now again, be careful because they've got copper 2 plus going to copper plus. That's positive 0.153, but that's not ours, right? We did copper 2 plus going to copper solid, and there is plus 0.34. So now, because we have two metals, right, after using that standard hydrogen electrode, we now have zinc solved and we have copper solved. So now I could pick something else out and match it with zinc or match it with copper, and I could find those half cells. And from there, I could just create an entire chart full of all of these standardized values based on that original hydrogen electrode value. Okay, so you can always come and check yourself using this chart to see, similar to the KSPs and the KAs, if you're solving for a value, you can come here and check. Now, there are going to be problems where you have to come and actually use the chart in order to obtain the values. Okay, and in a case like that, we would need to gather these values, and you have to determine which one should be the cathode and which one should be the anode. So that's what we need to talk about next, because if you hook them up the wrong way, you're not going to get any proper potential. And if you don't have the potential, then you're not going to have a useful battery. All right. So when we talk about this and you're on a chart like this, the more positive your half cell reduction is for the potential, the better suited it is at being reduced or being an oxidizing agent. All right. So I'm going to repeat that. The more positive a value, so here's the plus values right here. All right. The more positive a value is in terms of its reduction half potential here, that means that the better suited that compound or metal will be at being reduced. So it will make a better oxidizing agent. It should be the one being reduced. So let's put this in context of what we just saw. Suppose that I came to you on a quiz or an exam and I said, create a galvanic cell using zinc and copper. And I don't tell you whether copper is going to be the anode or the cathode, and you have to figure it out. But I just give you the net equation, and I say it's zinc with zinc 2+ ions, and it is copper with copper 2+ ions. And then I say, tell me the cell potential. Well, you have to know which is the cathode and which is the anode in order to plug it into the E cell equation. So if you come here and you say, all right, Professor Tomney gave me copper 2+ goes to copper. I come to the chart and I find that's plus 0.34. And then he also gave me zinc. So I come down to the zinc and I find zinc 2+ goes to zinc solid. That's negative 0.76. You then stop and you say copper is plus 0.34. Zinc is minus 0.76. Therefore, the one with the more positive value, in this case copper, is going to be better suited at being reduced, meaning it should be the cathode. All right. Any questions on this and how to use this chart? We're about to do an example in just a minute. Okay. So if there are no questions on that, let's go ahead. This is going to be the last example for today. So this is excellent. We've progressed very far for one lecture period here. All right. So bringing the whiteboard back up, here's the problem I want to work with. I'm going to give you two metals at a standard concentration, and I want you to find out the E cell. Right? So the question here is going to be, what is the E cell, the standard E cell, if I give you the following two? Right? So what I'm going to give is silver plus going to solid silver. That's one half reaction. And I'm also going to give you magnesium 2+, okay, is going to go to magnesium solid. All right, so what I want here, all right, is going to be the E cell. So the question is, which one of these should be the anode? And which one of these should be the cathode? So what I'm going to do, I'm going to give everybody a minute here. I'm actually going to go get a drink of water because my throat's starting to get dry from talking so much. I want you to go into that chart. So pull it up, go into the chart, find silver plus going to silver, mark down its value for its potential, go to magnesium 2+ and magnesium, mark down its value, and then figure out which should be anode, which should be cathode, and determine the E cell. So I'll be back in a minute and we'll discuss that. All right, so we have about 5 minutes. I am going to go through this briefly, and then I'll stop the recording just to take and field any questions that may be at the end of class here. All right. So going back, we want to take a look. Let's find the silver to start with. So silver, from an alphabetical standpoint, we're talking about the symbol. That's AG. So we need to come to the top here. I usually take mine out to 2 decimal places when I'm doing these calculations, and then we're doing plus minus, so you keep 2 decimal places in the answer. So that's how I'm going to do this for consistency as we're moving through here. So silver, gaining an electron and going to solid silver, is going to be 0.80. So you can see here you got the 0.7996. So I'm just going to round that up to plus 0.80. So that'll be my value for silver. And then I need to find magnesium. So I'll scroll down to the M section. Here's magnesium. I've got magnesium 2+ gains 2 electrons and goes to magnesium. And that is negative 2.37 if I keep 2 decimal places, right? Just a brief side note here, even though this is not what's being asked in this question. If silver has 1 electron being transferred and magnesium has 2 electrons in the transfer, this is not currently set up for a balanced equation, right? Now, I'm not asking you to give me a balanced redox here, but that should be a question you're comfortable doing at this point, all right? So, keeping those 2 values in mind, if I were to come back, I would say, all right, the silver was determined to be 0.80, and that was positive E cell. The magnesium was determined to be negative 2.37 E cell. So of the 2, the silver has the more positive potential for the E cell. So that's the way I'm going to set it up. The silver will be the cathode, which is what's being reduced. So I go ahead and I say standard E cell of this battery is going to be equal to 0.80 volts minus a minus 2.37 volts. This becomes added. So the E cell that you should have come up with in this problem is 3.17 volts. Okay. I could tell you right now, I will give you a quiz question like this. I will give you 2 metals and their half reaction. I will expect you to go in and find values from the table, and you should be able to discriminate which one is going to be the anode and which one is going to be the cathode, and then plug it into this. So this is outside of looking at the values on the chart, which let's say maybe takes you 2 to 3 minutes to gather that information if you're scrolling through. You then have another 1 minute of arithmetic. I'm not even going to call this algebra. And then you have your answer. All right, so if you have any questions on this, make sure to ask me. But these are very easy points right here on a quiz or a test when I ask you this sort of stuff. All right, keep in mind I could also ask you to draw a cell like this. So I could say, here's silver, here's magnesium, draw a galvanic cell. And then I'd like you to set up the beakers, and you would set up which one has the anode and which one has the cathode, and set up their individual metals. So you could have an electrode of silver, an electrode of magnesium, set them into their respective solutions, create a salt bridge, etc. And then obviously the half reactions. That's what we started this chapter with. All right. So I'm going to stop sharing now, and I'm also going to stop the recording.